Today we have another classic, and it is that if a function bounded on an interval from a to b is continuous, then it is Riemann integrable. That is a classic proof, very standard result. We don't even need functions to be continuous to be integrable. We also know that monotone functions, so functions that are strictly increasing or strictly decreasing, are also integrable, and even functions which aren't completely continuous, functions that have a finite number of discontinuities. So even a function like this, which has a finite number of jump discontinuities, this function would also be integrable. However, we also know that continuous functions are integrable. This proof is a bit harder, but this one over here is very classic. For the finite case, it's a bit harder. First of all, what does it even mean for a function to be Riemann integrable? Well, that just means bang. If we take the upper and lower sum of a function, bounded on an interval. So again, the lower sum, on each interval, this is an interval I. The lower sums are just the minimum points of the function in an interval. The upper sums, would be these red triangles, or the maximum points of the function in the interval. If we have that the upper sum, so let's say the upper sum of the function with our partition n minus the lower sum of our function with our partition n is less than epsilon. So if you can choose such a partition, fine enough that this is true, then the function is integrable, because basically that means the upper and the lower sums are identical. So we want to show that if a function is continuous, we can find such a special partition such that the lower and the upper sums will be less than epsilon. Now what we're going to need in this proof is, of course, we know that a function is continuous, and because it's bounded on an interval, we know that the function is going to be uniformly continuous. It's such a hard word to spell, continuous. What is the difference between continuity and uniform continuity? Because every function that is continuous is also uniformly continuous on a bounded interval. So first of all, let's just check continuity. If you already know the difference between uniform continuity and continuity, you can skip this part. I'll probably just make a video on the difference, because the difference is pretty hard to grasp at first. It took me like a while to grasp it. But basically, we know that the classic definition of continuity, actually I can just draw it first, is that for every x0 in the domain of our function, and for every epsilon greater than 0, we know that there exists a delta greater than 0, such that if for every, or basically I can say for every x, which is in the domain x0 minus delta, x0 plus delta, so so if we have our little domain here, if we have x0 here, if we pick the delta this big, this is x0 plus delta, this is x0 minus delta. For every x in this interval over here, we have that the absolute value of f of x0 minus f of x is less than epsilon. So for every x which is delta close to x0, we'll have that the difference in the functions will be less than epsilon. That's the classic definition of continuity. And again, it also has a classic, interpretation of the graph. So we have a function here. We pick the point x0, and then we look at f of x0. So then we pick a point x0, and then here, and then we also pick an epsilon greater than 0. Now we can say we can pick an epsilon this big. So this is f of x0 plus this epsilon, and again this is f of x0 minus epsilon. So now we can find our delta interval. Our delta interval will be here, x0 plus delta, and again here it's going to go to here. So again, this one is bigger, this one smaller, so we have to choose, if this is our delta, then we'll say this over here is our minus delta, so x0 minus delta. For every x in this interval over here, for every x that we pick in this interval, if we take the difference, between our function, we know that the difference between the function here will be between epsilon, because again, we're going to choose, for every x that we choose here, we're going to take the difference f of x0 minus, minus any point either over here or minus every point over here. And we know that difference always has to be less than epsilon, because again, this is our center point. We subtract either any f here or any f here, but that will always be bounded by this area over here. So we know this will always be less than epsilon if our x, if our x chosen is, delta close to a point x0. That's continuity. But then we have uniform continuity. And that is way more strict. Uniform continuity is way more powerful, and it's really cool. For uniform continuity, the definition is for every epsilon greater than 0, there exists a delta greater than 0, such that if 2 points x minus y, are delta close to each other, then f of x minus f of y are epsilon close to each other. And notice the difference here is, for the continuity, we picked an x0 and then we picked an epsilon greater than 0. So delta depends on x0 and epsilon. But here, all we pick is an epsilon greater than 0. So look, this is gonna make way more sense in a second. But now if we look at uniform continuity, we can have a function like this, and or let's say that a function that starts like this and gets steeper. Now we don't pick a center point x0. We don't pick any x0 point. We just look at any 2 points x and y that are that are delta close to each other. Again, x and y are in the domain of f. So it's not y as the y-axis. These are just this is points x1, x2, let's say. So any points, if this is our delta, we picked an epsilon greater than 0, so we know there has to exist a delta. Let's say that the delta is this big. So for any points that are this close to each other, let's say over here I have x. Or let's say delta is a bit smaller, just so I won't take over the whole graph. But let's say we have our points, our point x here and our point y here, and let's say delta is exactly this big. Well, if I look at the difference, if I look at f of x minus f of y, so this will be f of y, this will be f of x. This difference has to be less than epsilon. This difference over here has to be less than epsilon for any 2 points that are this close to each other. That let's say delta is this big. So now I can shift these points also here. This graph extends up. I can choose a point x and y here. Again, but my different points x and y, again, they are delta close to each other because again the delta is this big. So x minus y will only be this big. So now if I look at f of x and f of y again, they have f of x minus f of y has to be less than epsilon. So now I don't care. The difference here is that delta is only a function of epsilon. I pick an epsilon like this, and then the delta I choose has to hold for the entire domain, where my function is defined. This delta has to hold. But for continuity, delta is a function of x0 and a function of epsilon. So again, if I choose a different x0, let's say if my x0 wasn't here, but if my x0 was here, then delta might have been different. Because again, if the function gets really steep, and again if I pick an epsilon which is this big, well, if a function is really steep, then over here my delta is obviously going to have to be very, very small, because if my x0 is here, x0 plus delta, x0 minus delta will have to be very close to each other if I want f of x minus f of x0 to be epsilon close to each other. So that's the thing with continuity. Delta depends on x0 and epsilon. But here with uniform continuity, it doesn't depend on x0. The x and y can be chosen anywhere. And that's why we can say, for example, functions like x squared are continuous, but they're not uniformly continuous on the infinite domain, because x squared, for example, gets infinitely steep. So if I pick any epsilon, if my epsilon will be this big, if this is my epsilon, well, the steeper the function gets, obviously the smaller my delta range gets. So eventually, when the function gets infinitely steep, when the function will be almost a straight line, even if my epsilon is very big, the delta range will have to go to 0. So I can't pick a delta that holds for every single epsilon range, that holds for, if I pick it for x0, then again, I can pick, for whatever epsilon I pick, I can easily get a delta domain, and this delta domain will hold around x0. But I can't pick a delta that holds for every epsilon, because eventually, when the function gets infinitely steep, my delta will have to go to 0, because the function gets infinitely steep. I hope that makes sense. There's a lot of videos on continuity and uniform continuity. But if a function is on a bounded interval, if it makes sense to you, you're going to see that if a function is defined on a bounded interval, then it has to be uniformly continuous. That's just how it goes. So now we can actually move on with our proof. I think that took a bit too long. Maybe I'm not even going to include this part. Basically, in our proof, we're going to fix epsilon greater than 0, and we're gonna select a delta greater than 0, such that if x minus y are less than delta, we just talked about this. So if x and y are 2 points which are delta close to each other, then f of x minus f of y will be less than epsilon. But I can say it can be less than anything. I can say it can be less than epsilon b minus a, where again a to b is the interval of our function. Our function, we define it on the interval from a to b. So we only want it to be Riemann integrable from this interval. So I can pick that f of x minus f of y is less than any number. So I can say that it has to be less than a number epsilon over b minus a. Or again, b minus a, this will just be constant. This is just the length. Our interval goes from a to b. So this will just be the length of the interval where our function f is defined. So I can say that because the function is uniformly continuous, since it's continuous, it's uniformly continuous on this interval. And now I can select an n such that my partition b minus a over n will be less than delta. And now, what is this? Of course, to integrate a function, I have to choose a partition. So now, I chose a partition such that each interval of the function will have a length b minus a over n. So I split the function. Again, this is the classic thing you do with integration. Draw my function like this. A classic thing you do with integration, let's say this will be my interval. This can be my point, x0. This can be my point xn. So, x0 equals a, xn equals b. And let's say I split my function into intervals, this into equal length intervals. If n equals 3, let's say n equals 3, then each interval here, in will have length, b minus a over n, so over 3. So I'm going to split this function into 3 equal intervals. Again, n can be whatever. This is just how we partition our function. We want to choose an n such that b minus a, so that this length over here over n will be less than delta, so that each interval, realistically, if delta is a small number, I'm going to have to make the intervals very small, so n will have to be large. But basically, we can choose an n such that each interval size will be less than delta. So let's say delta is this big, and each interval will be exactly this big, and each interval will be the same size. That's very important. So now we have a uniform partition. I can say that this is a uniform partition of our interval a to b. So of size b minus a over n. And now by the Weierstrass theorem, the Weierstrass theorem is just a classic theorem that says on every interval. So let's say by how do you spell this? I should have checked how to spell this. By Weierstrass theorem. It's just, you can also prove it. I think I even have a video on it, but basically it just says that the Weierstrass theorem, it's a simple thing. If you have a function, and then if you look at an interval of the function, that at this interval there exists a point where the function has its lowest value. So example, this point, x min would be where the function has its lowest value, and then this point would be f max, and that's where the function, this would be x max, that's where the function has its highest value. So in every interval, obviously, the function has to take a maximum and a minimum. Here, f max would be here, and f min would be here. So every function, that just, on an interval, we can say that, by Weierstrass theorem, for every interval in, there exists points x min and x max, inside our interval in, such that, we can say that f of x min, let's say I can call it L, and that would be the, lowest value. So this would be the lowest value of f of x, defined in this interval in, on in. And then I can say that there also exists a point, x max, and, this I can call, L is for lower, and then U is for upper, and that would be the biggest. That would be the biggest value of f of x on in. So, and that's for each interval. So again, I can check for this interval over here. I can say that x min will be, let's say, this point over here, I think, kind of, and then x max will be over here. And now, the special thing I can say about this is, well, x max minus x min, they have to be at least delta close to each other, because again, each interval is size delta. X max and x min, again, this will be x min, this over here will be x max. They can never be, in the most extreme case, x max will be here and x min will be here, or vice versa. So their difference will be exactly delta, because each interval is, delta big. Or, if they're somewhere inside the interval, their difference, their distance from each other must be less than delta. So their difference must always be less than or equal to delta, because they're both inside the interval, so less than or equal to delta. So I know that, then it depends how you define your interval. It can either be less than or equal to. But because these points are, delta close to each other, we know that f of x max minus f of x min has to be epsilon close to each other. So it has to be less than epsilon over b minus a. Again, we defined this as our epsilon. So, I define this as L and I define this as U. So L minus U has to be less than epsilon over b minus a close to each other. That's how we define, that's uniform continuity. That is exactly using uniform continuity. If these 2 points are, delta close to each other, then again, f of x and f of y at this point have to be epsilon close to each other. That is exactly the definition of uniform continuity, which we are using here. And now our proof is basically done already, because now if we take the upper sum of f with our partition Pn minus the lower sum of f with our partition n, that is just going to be the sum of n equals 1 to n of f, and then of all the f x maxes where, this x max is defined on each specific interval. We can say x max, or you can say, for example, we can also just say, so it's more clear, f I max, so the maximum value of f, of the maximum value of f in this interval I. I max, where, first we'll have interval 1, then we'll have interval 2, we'll have interval 3, up to n, times, times the size xn, minus, this is the lower sum, n equals 1 to n, of f I min times delta xn. Again, this is just the classic, lower and upper sum. So we have our little, we have a function, and then we split it into intervals. And then, we obviously, I can just go down here and show it. So we split our function into intervals, and then we sum up, we sum up the rectangles. So we find for each, for the lower sum will be the function, the lowest value of the function defined on the interval. So that will be, that will be the height, that will be the height of this will be up to here of our rectangle. Then the size of the rectangle will just be the base will just be the interval size, delta x. So then delta x, times f of x, that's just base times height of each, and then so the lower sum will be the sum of all these lower rectangles, and the upper sum, will just be on every interval the sum of the highest rectangles. The base will be the same, but the height will change. The height will be the maximum of the function on each interval. So that's what we're doing over here. The lower sum minus the upper sum. Delta xn, again, these intervals have the same size. The size of the interval is b minus a over n. So that is just a constant. We can take that out of the sum. So we can take these out of the sum. So then we just have the sums, subtracted from each other. So basically this upper minus lower sum will just be b minus a over n times the sum from n equals 1 to n, again, of f of I max minus f of I min. And we just said that x max and x min will just be L minus u for each interval, so for each interval n from 1 to n. And now, since on every single interval, f of x and f of x max and f of x min will be inside this interval, we don't know what f of x max minus f of x min will be. It will be different for each interval. However, since every x will be less than every two pairs of x max and x min for every interval will be delta close to each other. Will be delta close. They'll be less than delta close to each other. That means that f of x max minus f of x min will be epsilon close to each other. So we don't know what the difference L minus u will be for each interval. We don't know what this difference will be, but we know that for every interval it's going to be less than epsilon over b minus a. That's what uniform continuity tells us. So we don't know what this will equal, but we know that this will be less than b minus a over n times the sum from n equals 1 to n of, wait, let me just get rid of this, of, well, we don't know what this is, but we know that this will be less than epsilon over b minus a. So we know that since this is less than this, this will be, this over here will be greater. So we know that will be less than this, and each of these values will be, we upper bound them with this over here for every interval. We do that by uniform continuity, and again, we just sum this n times. Again, so we do this plus this n times. It's just a constant. So what we get is that this over here will be exactly equal to b minus a over n times, again, just n times epsilon b minus a. And now we can see the n's cancel, and now we can see why we picked epsilon over b minus a except for just epsilon, so that this cancels. And what we get is epsilon. So we just got that the upper sum of f pn minus the lower sum f pn is less than epsilon. That means the function is Riemann integrable. We found such a partition. Of our function, b minus a over n. So there exists an n such that this partition will be less than the size of this partition will be less than delta. And because it's less than delta, we can use uniform continuity. We can create this bound. We can get this over here. So we can show that there exists a partition such that the lower bound and the upper bound are infinitely close to each other, which means that they have to be the same. So we just show that the function has to be Riemann integrable if it is continuous. It is a pretty clean proof. I guess, the continuity and uniform continuity is a bit of a, well, I want to say advanced concept, but it takes a while to grasp. I don't know if my explanation was that good, but when I was trying to understand it, I just looked at a bunch of videos, I got every single perspective. I watched like 5 different YouTube videos, read like 2 different texts, and everyone explains it a bit differently, and then eventually like you just get it because you looked at so many different perspectives. So that's my kind of advice for every math concept that's a bit harder to get. But yeah, that is it. I hope it makes sense, and thank you for watching.